The tangent to a circle theorem states that a line is a tangent to a circle if and only if the line is perpendicular to the radius drawn to the point of tangency. Here comes the first way of proving our theorem. To prove an if and only if theorem, we are going to prove it from left hand side to right hand side and the other way around, which is from right hand side to left hand side. If we can prove both sides correct, then we can say that our first way of proving this theorem is true. Now let's prove the theorem from left hand side to right hand side, which starts for the first sentence. If a line is a tangent to a circle, we then form circle P with radius O and we draw another line AB that intercepts the circle at point C, and then we connect the radius of this circle to the tangent and label it R1. We then do the same thing to the other circle Q with origin Z. We connect the radius of this circle to the tangent line AB and label this radius R2. Please note that this tangent line AB will be the common tangent for circle P and circle Q. Now we are going to enlarge the part C, the intersection point C. This line AB and this line OG is intersecting each other. This line OG, remember, is formed by radius R1 and radius R2, which are the radius of circle P and Q. And this common tangent line AB is an important line to remember. They both intersect at point C. Now, if I draw an arc here, do you guys still remember what is the total degree of a straight line? It is 180 degrees. But if we intercept a line with this straight line, then the degree at each side of it will be 90 degrees. So I am writing this as 90 plus 90 degree equals to 180 degree. And with that, we can prove that this radius R1 from circle P is 90 degree to the line AB, and this goes same with the radius of circle Q. And with this, we have proven that the line is perpendicular to the radius drawn to the point of tangency with direct proving method. Now let's prove our theorem from right hand side to left hand side, which starts with a sentence: if a line is perpendicular to the radius drawn to the point of tangency. We first form a circle W with origin O, and then we connect the radius of this circle to 2 points P and Q. And then we are going to extend these 2 points P and Q to a same point that lies outside the circle, which is point S. And then we connect the origin of this circle with the point S with distance M. With the first sentence of a statement, they say that if a line is perpendicular to the radius drawn to the point of tangency, we can now label angle OQS and angle OPS as 90 degrees. With that, we have formed two right angle triangles, OQS and OPS. Let's enlarge these two right angle triangles and see what happens next. By Pythagoras theorem, we can clearly see that distance QS is equals to square root of m squared minus r squared, and this goes same to the distance PS. PS is also equal to surd of m squared minus r squared, and we can conclude that PS is equals to QS. So when we say PS is equals to QS, this suits the two tangent theorem, which states that PS will equal to QS if they are the tangent that extend from a same point that lies outside the circle, which is point S. So with this, we have proven the following sentence of our statement. It says that the line is a tangent to a circle by direct proving method. Here comes the second way of proving our theorem. Please remember that normal to radius of a circle is always perpendicular to the radius. So in this second way of proving, we are going to find three things. First will be the tangent of a radius, and with this tangent found, we are going to use it to form the equation of normal to the radius. And then lastly, we are going to find the equation of tangent to a circle. If we are able to find that, equation of normal to a radius is the same with the equation of tangent to a circle, then we can say that normal to a radius is equals to the tangent of a circle. And please go back to the first thing that we mentioned. Normal to a radius of a circle is always perpendicular to the radius. If we can prove that tangent to a circle is equal to normal to a radius of a circle, then the tangent to a circle is also always perpendicular to the radius. Here comes the circle. Now, let's draw the radius of a circle to any point and label this as r. And then we are going to form a right angle triangle and label this angle as theta. From that diagram, we can see that the x coordinate is equals to r cos theta and the y coordinate is equals to r sin theta. With these both the coordinates found, we can form the tangent of the radius, which is equals to tangent theta. With this tangent found, we can also find the tangent of the normal to this radius, which is negative 1 over tangent theta. And lastly, we are going to use this tangent of normal to radius to form the equation of normal to radius, which is y equals to negative 1 over tangent theta x plus r over sin theta. Next, we are going to find equation of tangent to a circle. We firstly form the equation of a circle, which is y squared plus x squared equals to r squared. And then the tangent of the circle can be found by differentiating this equation with respect to x, which is dy dx equals to negative x over y. Lastly, the equation of the tangent to a circle can be formed by substituting the x coordinate and y coordinate into this equation, which is y equals to negative 1 over tangent theta x plus r over sin theta. And we can prove that the equation of tangent to a circle is the same with equation of a normal to a radius. So we have proven that the tangent of a circle is equal to the normal to the radius, and we can say that the tangent of a circle is always perpendicular to the radius. Here comes the third way of proving our theorem. Please do remember the property of tangent is that when a point is extended into a line, the line is only considered a tangent to a circle if the line intercepts the circle at only one point. So, there are three possibilities for the point to lie in relation with a circle, which is when the point lies in the circle, on the circle, or outside the circle. Case 1. When the point lies in the circle. No matter how we extend the point into a line, the line will always intercept the circle at 2 points, so it is not tangent to the circle. Now, case 2. When the point lies on the circle, if we extend the point into a line, the line will only intercept the circle at single point, hence it is a tangent to the circle. Case 3. When the point lies outside the circle, if we extend the point into lines, the lines will always intercept the circle at single point, so this is also a tangent to the circle. So now, case 1 is out and we are only considering case 2 and case 3. Now, let us consider case 2 when the point lies on the circle. Let us first make an assumption that the radius is not perpendicular to the tangent line. I will demonstrate to you when we say that the radius is not perpendicular to the tangent line, there will always exist another point on the tangent line that is perpendicular to the origin of the circle. Let us go back to the circle that we have drawn and we label the center of this circle as O. After we connect the radius to the point C, remember, we are now under the assumption that the radius is not perpendicular to the tangent line. So, there will always exist another point on the tangent line AB that is perpendicular to the origin of this circle. And now, let's label the point as point D. As what we have known, the total internal angle of a triangle will be 180 degrees. And from the diagram, we can see that angle ODC is equal to 90 degrees, which means the other two angles of the triangle will add up to 90 degrees. And we can conclude that angle ODC is always greater than angle OCD. Now, let's apply Pythagoras theorem to continue our following improvement. From this right angle triangle, we can clearly see that angle WPK is always greater than any other internet angle of the triangle. So, and we also can clearly see that distance WK is the greatest among all the other distance. So, we can conclude that when we say angle WPK is greater than angle WKP, we can also say that the distance WK is greater than distance WP. If we apply this theorem to the equation that we have formed just now, we can conclude that distance OC is always greater than distance OD. And if we add a point Q between distance OD, we can say that distance OC is always greater than distance OQ plus QD. And from the diagram, we can see that OC and OQ are both the radius of the circle, so they are equal. And finally, we are going to make an equation which states that 0 is greater than QD, which is a contradiction to the fact that the radius is perpendicular to the tangent line. Now, let us consider case 3 when the point lies outside the circle. We are labeling this external point as point C, and let's label the origin of the circle as O. Then we connect the radius to point A and B. Now, let us enlarge the upper side of this circle. From the diagram, we can see that point A is the closest point on line AC to the origin of the circle, which is point O. Let's give an example. If there exists another point E that lies on the line AC, the distance between this point E and the origin of the circle will be radius plus any other constant value, while point A is just a radius away from the origin of the circle. This applies the same to the bottom part of the circle. Point B is the closest point on line BC to the origin of the circle, which is also just a radius away from the origin of the circle. So, it is a fact that point A and point B are the closest point on line AC and line BC to the origin of the circle. Now, let us make an assumption that the radius is not perpendicular to the tangent line. Let's first form a right angle triangle that connects the tangent line AC. As what we have mentioned at the previous slide, if we say that the radius is not perpendicular to the tangent line, there will always exist another point on the tangent line that is perpendicular to the origin of the circle. So, by Pythagoras theorem, we can clearly see that r, which is the radius of the circle, is greater than y. So, this applies the same to the other side of the circle. Hence, we can conclude that point Q and point W are the closest point on line AC and line BC to the origin of the circle, which is contradiction to the fact that point A and point B are the closest point on line AC and line BC to the origin of the circle. Hence, we have proven case 3 by contradiction.